Okay, so welcome back to this, sadly, our final part of Journey Across the Universe. You know, I can't quite believe this is the final part. It seems time has flown by, which is quite apt, really, as the final lesson is all about time. Now, time is a really complicated thing, and we haven't got time, no pun intended, we haven't got time to describe everything we know and what we don't know about the nature of time. But I can talk a little bit about some of the things that are interesting, and hopefully it'll spark some little grey cells inside your brains that make you want to go and find out more about time, like you did about the universe, the galaxies, and everything else. So I've had a really fascinating time. I hope you have, guys, too. We left Earth. We explored the solar system. We looked at our galaxy and other galaxies. What else did we do? We've seen exactly how big the universe is, and it is big. It is massive. It goes on forever, practically. As far as we're concerned, it goes on forever. We discovered last week that the chances of there being life out there are really incredibly high. So much so that personally, I'd say that there definitely is life out there. Now, traveling the universe. Oh, that's it. Look at that. That's an amazing slide, that one. All about time. Oh dear, excuse me. Now, for me, traveling the universe is just the greatest adventure you could possibly have. And of course, we now know how big it is. We need to work out how we're going to actually travel the entire universe. Because, as you know, the universe is very, 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 very big. In fact, to travel across it at the speed of light, it would take 93 billion years. Now, I don't know about you, but I don't have that much time to spare. And on top of that, by the time we got anywhere, it would not be the same as when we left. And we'll go into that later. And when we got back, 93 there, 93 back, the Earth would be 186 billion years older than it is now, and it wouldn't actually be here anymore. That's the problem. So by the time we got back, the Earth, even if it did exist, which it probably wouldn't, we wouldn't really find anything here. We'd have to put a missing poster up saying we've lost the Earth. It was last seen in the solar system. It's a blue-green planet, and can you let me know if you find it? So we've got to travel faster than light to get anywhere. Except there's a little problem about that, because nothing can actually travel faster than light in the universe. Nothing, not even light, can go faster than light. There's a speed limit, 299,792,458 meters per second. So every second, so the few seconds that we've had this lesson running for, which is probably what, about 7 minutes. So 7 times 60 times that is how far light has traveled since we started. Ooh, who's got a raised hand? Let's answer the question then. Who's a raised hand?
I have got a raised hand. So what if we can't go faster than light, maybe we could go the same speed as light?
Well, in theory we could. In practice, it takes a lot of energy. We'll come on to that in a minute. But do not worry, because that doesn't mean we can't necessarily get anywhere before light would. It's just that we can't travel in normal space. And that is the really interesting thing. So if all that sounds a bit weird, then that's because it's all a bit weird. So we need to look into the nature of time itself to find out how it might be possible to travel those great distances without breaking the laws of physics. So that leaves us with some questions. Why can't we go faster than light? How can we get over this speed limit? Are there any shortcuts across the universe? And in order to answer these, we need to start at the very beginning and answer one question first. What exactly is time? We all know what time is, don't we? But then we don't. We know that it takes a certain amount of time to go to school. We have a certain number of hours in the day. We've got, we can measure how fast things go. You know, we can measure how old things are. We can measure time, but we don't really know what it is. It's a bit like saying what's length, what's height, what's depth. Well, I can tell you how tall I am. I'm 6 foot tall. But what is tall? It's a bit of a funny question. Now, There was a great thinker back in a long time ago. His name was Saint Augustine. He was a great thinker, as I say, and he asked this same question 1,600 years ago. And he said he just couldn't understand or explain what time was. He said, we all know what time is because we experience it. We cannot actually say what it is or how it works. And that's a question that nearly 2,000 years later, we still can't really answer. We can measure it. It's easy. Perhaps we could look at how we measure it then. We use clocks every day. They tell us when it's time to get up, when it's time to eat, when it's time to go to school, time to come home, time to switch on the TV and watch Doctor Who, and time to go to bed. So clocks today are incredibly accurate. They're more accurate than the turning of the Earth and the time it takes the Earth to travel around the sun. So much so that we need a leap second every so often. Our clocks keep better time, and if we didn't make adjustments, they go wrong. So we actually have two main types of clock, okay? Man-made and natural ones. So natural clocks, what are natural clocks? Well, natural clocks include the movement of the Earth with the stars, the sun, the moons, the planets, all measuring out hours, days, weeks, months, and years. They also include things in nature like plants, seasons, and animals hibernating. They're all clocks. They all happen at regular intervals. Of course, that's great. We can look outside and say, oh, well, the squirrels are digging up their nuts, or the birds have come back from Africa, so it must be spring. The leaves are falling off the tree, so it's probably half past autumn. Now that's great, but it's not very accurate. It's good to know when to plant crops or when to start getting your woolen jumpers out from the cupboard at the back of the bedroom that you put them away in the summer because it was too hot to wear jumpers. But it's not very good for timing when your eggs are boiled or when the cake should come out of the oven. We need something a little bit more accurate and a little bit more precise to measure small amounts of time. So we have man-made clocks. Oops. So these are things that have been constructed, and they measure out the passage of time in the same unit. And they have they've been around for a long time. Over 4,000 years ago, for example, the Egyptians used an obelisk to cast a shadow. They're known as shadow clocks. They had sundials, water clocks that measured the passing of time by the flow of water. Passing into a stone vessel. When the stone vessel filled up, they know so many hours have gone by, so many minutes. Now, we have a 24-hour day. When you think about that, why do we have 24 hours in a day? Why not 10 or 100? Or why is it 24? Well, that comes from the ancient Egyptians. Now, they effectively divided the daytime into 10 hours, okay? Which you think, yeah, that makes sense, but that's just the daytime. And they measured that with their shadow clocks and sundials. But of course, in the morning and the evening, there isn't much sun, but it's kind of light. It's a twilight time. So they added a twilight hour at the beginning and another one at the end of the day. So that gives it 12 hours. And then they divided nighttime into 12 hours. And they based that on the stars, looking at the stars, observing the stars. So the Egyptians had a system of 36 star groups they called decans. Don't know why. Sounds like deck chairs. So they were chosen so that any one night, one decan rose 40 minutes after the previous one. So they could time 40 minutes, effectively. So tables were produced to help people determine the time at night by observing these decans. So it'd be a picture, and we'd say, right, when we can see those stars, 40 minutes later, we'll see these ones. 40 minutes after that, we'll see these ones. And you can mark off time. It's fairly accurate as well. So in the Egyptian system, the length of the daytime and the nighttime hours were unequal and varied with seasons. So they actually had longer hours in the nighttime in the winter and shorter in the summer, that sort of thing. So in summer, daytime hours were longer than nighttime hours. So that we still had 12 hours in a day, or 10 plus 2, but they were actually longer hours. That seems a bit strange. You go to work in the summer and you work longer hours than you do in the winter. It kind of makes sense in a way. In the winter hours, it's the other way around. So we had shorter hours in the day, but the same number of hours. But it was the ancient Babylonians who gave us hours and minutes. Now, the Babylonians had a real fascination for the number 60. They loved it. So we not only kept hours and minutes divided into 60, but also their division of a circle into 360 parts of degrees. It's likely that the Babylonians were interested in 360 because that was their estimate for the number of days in a year. We know it's about 365 and a little bit, but 360 was close enough for them. So yeah, so they had this fascination with 60. So all of the great civilizations of the past used the positions of the sun or stars to tell the time. It's obvious, really, isn't it? The sun comes up in the morning, goes down in the evening. Stars move across the sky regularly, so we can measure things by them. And they're really, really accurate. Ancient astronomers could tell the time to within 15 minutes. Look at the stars, and then it was somewhere between 11:45 and 12 o'clock, and 12 o'clock and quarter past. And they got really good at that. But again, 15 minutes when you're boiling an egg, that's not really going to be accurate enough because your egg's either going to be still raw or it's going to be hard boiled. And I like it where you can dip your soldiers in the egg. There you go. I mean, anyone can roughly tell the time simply by looking at where the sun is in the sky. You know it's over there, it's the morning. As it goes up, it gets to the high point, it's 12 o'clock, and it goes down again. It's about halfway between 12 and there, so that makes it about 2 o'clock, that's 4 o'clock, and you know when the sun's going to go down. You can tell it. But we want to be really, 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 really ultra accurate, and we can be these days. This is the world's first, what they call an atomic clock. They are the most accurate. Now, how do they work? Well, they rely on the fact that all atoms vibrate or wobble incredibly accurately. I mean, really accurate. For example, a cesium atom vibrates at precisely 9,192,631,770 times every second. So as a second goes past, a cesium atom has vibrated nearly 10 million times. That's fast. But we can measure that vibration. And that's exactly what we do. So we set a computer to count those vibrations. We can measure 1 second incredibly accurate. Not to mention that we can measure time accurately to within 9,192,631,770th of a second. Enough to ensure that we could tell who won a race that looked like a dead heat. And if we use this resonance, as it's called, this wobbliness, to measure time, we get clocks that are accurate to 1 second in 20 million years. That is that the clock will only be out by 1 second after 20 million years have gone past. But measuring time, of course, is only half the story. Time's also an experience. By that I mean it's not simply something that is just there. We see things change as time passes. And we have something inside us called a biological clock. Now, flowers grow, they bloom. Babies are born. They grow into children and then into adults. We each have our own internal biological clock. Now, your heart beats on average 70 times a minute. Our moods, alertness, our appetites, they follow regular patterns. You wake up hungry for breakfast, you get hungry at lunchtime, hungry in the afternoon, hungry later at night. So it depends on the time of day, the lunar cycle, that's it, how many times the moon goes around the earth, or the season. Now, our biological clocks seem to be intimately associated with a group of nerve cells in our brain. It's in a part called the, get this, hypothalamus, okay? So there's a part in your brain, and it's linked to your eyes, and it also regulates many of your bodily functions through chemicals called hormones. It controls your temperature, your cycles of sleep and wake, and it plays a very important part in controlling a daily rhythm. Now, all creatures have a biological clock. Some of them are so good we can use them ourselves. When certain flowers open their petals at certain times of the day, and it's possible to plant a flower clock in order to put this in your garden, basically, and you tell the time by it. So you plant those various plants around a circle, and you know what time it is from 6 in the morning to 6 in the afternoon, because that's when the flowers open and then close again. And some cycles are not based on the length of a day, a week, or a year even. Now, there's an insect called a cicada. That's a cicada, once a full adult grown insect. But its grubs, its little baby ones, remain under the ground for 17 years, an odd number, 17 years. And suddenly, after 17 years, thousands of them emerge at the same time. They climb trees, they mate, they have babies, they lay the eggs, and then they die within a few hours. And the whole cycle starts again. So 17 years as little grubs under the ground, and less than a day as an insect, and then they die out. And that happens every 17 years. Then there's the fact that even without being able to see a clock or the sun or flowers or anything, we can still sense the passing of time. So we also have something called psychological time, a time that's in our head. It means how we experience time, the passage of time. So imagine yourself sitting in a room. There's no windows, no sound, nothing, no light coming in, nothing that changes. It's an empty room. But you can still sense that time is passing. And some people are very accurate, so accurate at estimating how much time has passed. Others not quite so. But our psychological clocks can be fooled quite easily. They seem to speed up and slow down. Have you ever thought, when it's a few days before your birthday or Christmas or Easter or something, then the days seem to go really, really slowly. Yet your birthday itself and Christmas Day, well, they just whoosh past in what seems like seconds. Or maybe the 2 weeks before the summer holidays seem to drag and drag. It's like, oh, when's the summer holidays? When's the summer holidays? But when the summer holidays come, they're over all too quickly. Maybe you have been to the dentist or a fun fair. So a few minutes in the dentist chair seem to last hours, particularly when he's prodding and poking in there. It's like, oh, when's he going to stop? This is taking forever. But then you can spend a whole day at a theme park, and it seems like you've only been there a few minutes. There's not enough time to get on all the rides. It goes fast, 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 fast. Now, remember our old friend St. Augustine? Well, after he calmed down a bit from his initial panic over what time was, he decided it was all in his mind. He said, time doesn't exist, not outside the head. Later thinkers also agreed with this, but is this right? Does time only exist in here? Well, we can look at the universe and look at it in terms of time. This is where it starts to get really interesting. Because we have something called cause and effect. Now, have you ever had a disagreement, an argument with a friend about something that happened? I'm sure you have. Maybe you think someone did something differently, or that one person did a thing rather than another person. You can disagree about who broke a cup or a mug, say, but there's one thing you can never argue about, and that is the order in which things happen. Say you come across your favourite toy and it's been broken. You knew it was okay when you last saw it. Your younger brother also agrees with it, younger sister or whoever. He says it was okay last night, and he says you broke it, and you say he did. Well, maybe it was him, maybe it was you, or even someone else. But there's one thing you can't disagree with, and that was the fact that yesterday it was okay, and today it's broken. This is because something can't be broken until someone breaks it. Seems obvious, but when we think about it, that's partly to do with time, isn't it? Things happen in a certain order. Time has a direction. So let's think about this. Let's think about somebody dropping the glass. You drop the glass, it breaks. That's what happens. You will never, ever have a glass that's broken and then somebody drops it. It's just impossible, isn't it? The glass can't go back to suddenly being whole again and then re-break. It's either broken or it's whole. It's whole before it's broken, after it's dropped. That's a certain order, and it always happens in that order, cause and effect. More importantly, the person who dropped the glass must have dropped it before it was broken. The glass couldn't be broken and then somebody dropped it. It's called cause and effect, as I say. And it's a really important idea when it comes to studying time as a scientist, as a physicist. And this is where it gets a little bit complicated. So time is not simply what the clock says, or something that's just in your mind. Time is a very complicated concept. So when did it start? When did time begin? Well, it began at the point the universe came to be. There was no time before. Asking what was time was like before the Big Bang is like asking, I don't know, what's further north than the North Pole? There isn't anything. There is no further north than the North Pole, further south than the South Pole. So time is actually part of the universe as much as space is. Indeed, it's impossible to understand the universe without describing it in terms of space and time. Now, physicists have a special word for this. It's called space-time. Now, space-time is a way of showing time and space together on a two-dimensional chart. Basically, it's a way of thinking of the universe not in 3 dimensions, but 4. So we normally think of describing shapes in terms of how tall, wide, and deep they are, like a cube. Similarly, we can plot the location of that cube by using coordinates. So I could say that that cube is, let's say, 5 meters to the east of me, 6 meters north, and 3 meters above me. So the east where I'm sitting at the moment is that way. So it's 5 meters that way, 6 meters that way, and 3 meters above me. So it's over in that direction. That's dimensions. It's like plotting things on the chart. Okay. But the cube exists in time as well. So you could add a 4th dimension, time, as well. That way we can not only tell you where an object is, but also when it is as well. We need to plot things in time and space. So if it was there, if it was at position 1 at 3 o'clock and 5 minutes past 3, it was there, and then 10 past there, we're showing time as a direction, which kind of makes sense. We can show that on a timesheet here. So we've got, let's say we can collapse that down, and we put the 3 space dimensions going up the side, calling it position X, and where it is in time going across the bottom. So we can show where something is in time and space. So this is the cube here, standing still. Actually, no, it's moving in space, sorry, but not time. And this is moving in space and time. So time can be thought of as like another dimension, an additional dimension to the 3 we usually think about. It's really just another part of the physical universe. So time is part of the universe. So the next question, what time is it right now? Okay, if I was to ask that of everyone in the world right now, I'd get different answers. Now, it was once believed that time was an ever-flowing stream from the past to the future, but we now know that's not quite right. Time is not the same everywhere, and I'm not talking about time in France and Africa and India and America, because we know about that. But let's talk about Albert Einstein, famous scientist, famous physicist, mathematician. He did some thought experiments about the nature of time. There he is, Albert Einstein. He thought about what would happen if you traveled at speeds near the speed of light. Through his ideas and using some pretty complicated mathematics, he showed that when you travel very fast, and this answers your question about can we travel at the speed of light rather than faster than it, a number of things happen when you do try and get near the speed of light. So in 1905, over 100 years ago, 115 years ago, Einstein published his famous theory of special relativity, which put forth a startling idea, an amazing idea. He said says no preferred frame of reference. Everything, even time, is relative. What does that mean? Preferred frame of reference. It means that what you see and experience is unique to you, and someone else would see it from their perspective, from their point of view. So 2 people looking at the same thing don't always see the same thing happening. May not agree with what you see, okay? So you might see something and someone else will say, no, that was different. And we do that all the time, don't we? We watch a TV program and somebody else sees something that you don't in it and picks up on the plot. We could ask about a car you saw, and one person will say it looked red, someone else will say it looked blue. We're not talking about that type of thing. We're talking about how the universe itself looks different depending on where you are, and more importantly, how fast you're traveling. It's called a frame of reference. So in this picture here, which one of the person is correct? I'm standing still. Wait, no, you're not. Hold still. Well, that person in red is standing still, but they're on something that's moving. They might not know that thing is moving, so to them, they're standing still. Whereas the person on the outside can see the person moving because they're moving with the trolley that they're in. So you can see how, depending on what you're looking at, where you're looking at it, things can appear differently. There are two important principles underpinning his theory. The first states that the same laws of physics apply equally in all constantly moving frames of reference. What does that mean? That's a bit... It means that although we see things differently depending on where and when we are, the laws of physics still hold true. So although we can't tell who's moving and who's not, the laws of physics, science still works. So our broken glass will still not break until after it's dropped. Never. The order will not have changed, but we might see it dropped and broken at different speeds and times. I may see the glass dropped after you, but it will not break after the drop for both of us. I mean, it will always break after the drop for both of us, but we might see the drop happening at different times. That sounds very complicated, but if you think about it, if I was far and far and far enough away from you, we could still see the same person dropping the glass. Because light takes time to get to me, if it takes longer to get to me than it does to you from where you are, because you're nearer the person dropping the glass, then you will see the glass dropped first and I will see it dropped afterwards, but it will still be dropped and then broken. It's a bit like thunder and lightning, if you think about it. If you're nearer a storm, you hear the sound of the thunderclap before someone hears it further away. Now, normally, light, you can't tell the difference because the storms are so close. But if you are traveling at the speed of light, or you're far enough away, then you would actually see the flash of lightning happen after me or before me, depending if you're nearer or further away. And that's what Einstein's always saying. Although things happen the same way, they appear different to different people, depending on what speed they're going at and where they are. But time still goes in the same direction. Now remember, the speed of light is, we'll round it up, 300,000 kilometers per hour. That's fast, and it's constant. It doesn't matter what you're doing, where you are, the speed of light, it's not just a barrier, it's always the same. It never changes. And that means even if you are traveling near the speed of light from you is still the same. Wow, that's interesting, isn't it? So the speed of light is independent of how fast you're going or which direction you're traveling in. So if Superman were to chase a beam of light at half the speed of light, then the beam would continue to move away from him at exactly the same speed, the speed of light. Now that seems odd, but it means the speed of light is a constant for everyone, everywhere, which leads us to the conclusion. Now pay real close attention to what I'm going to say now, okay? It's not light that changes, but time itself. If light speed doesn't change, but your speed does, then that means when you travel very, very fast, it's not light that changes, time itself changes. Time slows down or speeds up depending on how fast you're going and how fast the other person is going. Seems really simple, doesn't it? But they have some real mind-blowing implications. One of the biggest is represented by Einstein's famous, probably the most famous equation in physics, E equals mc squared. Now, E stands for energy, m is mass, c is the speed of light. And according to this equation, mass and energy are the same thing. They can be changed into each other. So energy is just mass that's moving really fast, and mass is just energy that's slowed right down. They're the same type of things, but there's a barrier, that speed of light. Now, because of that, the energy an object has, due to its motion, will increase its mass. So the faster something goes, the heavier it becomes, essentially, greater mass. Now, that doesn't happen at normal speeds. It does, but it's so imperceptible, you can't detect a difference. But if you were to move very fast, say 10% the speed of light, 1/10 the speed of light, your mass would only be about 0.5% more than normal, a very tiny bit. But moving at 90% the speed of light, your mass will double. So this is what it looks like. So if I am approaching the speed of light, then my mass will rise really fast. So if an object travels or tries to travel at the speed of light, 300,000 kilometers per second, its mass becomes infinite, and so does the energy required to move it. This is why, as you asked earlier, you cannot travel faster than light or even get anywhere near the speed of light, because you need more and more energy, because the faster you get, the more massive you get, the more energy you need, to the point where to travel at the speed of light, you would need all of the energy in the universe and more. There's not enough energy to get 1 kilogram of stuff to travel at the speed of light. That's weird. Oops, my words have gone. That's better. Another thing also happens as you approach the speed of light as well. Something physicists call time dilation, which describes how time runs more slowly for objects moving rapidly. Think about that. The faster you go, the slower time passes. So remember, in the middle of a black hole, time slows down. And if you travel at the speed of light, time effectively stops. If you flew on a rocket traveling 90% of the light speed, the passage of time for you will be halved. Your watch would advance only 10 minutes, while more than 20 minutes would have passed for someone back on Earth. If we were to travel far enough and fast enough, then this would mean we would return to Earth having aged only a few years ourselves, only to find that those we left on Earth had aged considerably more. Your children will be older than you. Your grandchildren will be older than you. Since then, through the experiment, Einstein has been shown to have been absolutely correct in those theories. And we have to make sat-navs, navigation devices that actually take time dilation into account, or else they wouldn't be accurate. Now, this is because the satellites they use to pinpoint their location are running at a different time rate to us on Earth. And that's due to another bit of Einstein's theory. Something else that affects time, and another thing that Einstein worked on, is gravity. Our old friend gravity again. I mean, gravity has been in every single one of these sessions so far. So where can we find some really strong gravity to examine this idea? Well, of course, the strongest gravitational fields in the universe can be found in black holes. Now, they're so massive that they severely warp the fabric of space-time. That means that they bend the universe. They change the universe's shape. And they bend space and time, because space and time are all combined. Remember, space-time is the idea that time and space are basically the same things, 4 dimensions. I got a question from Sean. Go on, Sean.
Does that mean black holes can go faster than light?
Black holes themselves can't go faster than light, but they have an effect on light in so much as they slow it right down so that light can't actually escape from a black hole.
Then why does the space and time rip and stuff, like when it goes, it like changes it?
Because when you have gravity, actually it isn't gravity that bends space-time. Space-time bending by incredible mass, dense mass, bends space-time, which causes things to change direction, which is what gravity is. So although we say gravity is a force, that force is there because it bends space-time. So if I try and go this way, then it's a bit like trying to walk across the surface of a, I don't know, I'm trying to think of something where it's like that. It's a bit like trying to walk up a slope. Okay, and if I'm on a bicycle, say, traveling on a slope, then the slope tends to make my bicycle go off to one side, doesn't it? Because that's the way it goes, because gravity's pulling you down. So it's kind of like that, but what's happening is it's a massive gravitational field that actually bends the whole of space. It's quite a complicated, if you can imagine a big rubber mat stretched out, which is the universe, all 3 dimensions into one, and I put a very heavy bowling ball in there. If I try and roll a little marble past the bowling ball, it's going to get bent in towards the bowling ball and go down into the dent in the rubber mat. Okay, that's what it's doing to space-time. That's what gravity is. So space-time is the idea that space and time are basically the same things, 4 dimensions. So for that reason, an observer inside a black hole experiences the passage of time much differently, much more different than an outside observer. So imagine you want to investigate a black hole by shining a light towards it and measuring the time that elapses before the light is reflected back to you. Unfortunately, you'll be waiting a very long time, forever in fact. That light will appear to continually slow down as it approaches the black hole, ultimately reaching a complete dead stop at something called the event horizon. Sean's got another question.
Oh, sorry.
Yeah.
See, like if you get sucked into a black hole, is there a possibility that like you can survive, and if so, like where would you go?
Good question. Ultimately, no, you won't survive, but it could be less stressful than you think. There's a point in a black hole where you will die, so you could go up to the event horizon and come back out again if you had enough energy, but if you cross that event horizon, then you disappear out of space and time. That really is true. So let's send someone into a black hole. Let's send Sally. Here's Sally. Hello, Sally. She wants to do a much more hands-on investigation of time inside her black hole, and she decides to dive towards it. So before she leaves, Sally agrees to flash a light back every second. So she puts a flashing light which flashes once a second back towards where we are outside the black hole. So from what we look at Sally, she appears as she goes in to slow down. She gets nearer and nearer the black hole, and the time interval between her flashes of light gradually increases. So she's sending them out every second, but we're starting to see them with longer intervals, more than a second. And eventually, the light she's shining back at us gets dimmer and it gets redder. Okay, so it starts off as a white light and it gets redder and redder. So according to us, Sally never actually goes into the black hole. She just travels more and more slowly as she approaches it, and then we'll never actually see her reach the point of no return. Time comes to a standstill at the event horizon, and we will never really see her fall into the black hole. So strangely enough, even this surface of the star we can't see. We just can't see anything at that point. It's frozen in time. What does Sally see as she looks out when she's falling in? Well, that's even stranger. To her, the whole universe seems to speed up and contract. She sees the whole universe, like watching it on video, speeded up. Okay, it's going faster, faster, smaller and smaller. It's like somebody's pressed fast forward with the speed, but it's getting faster and faster and faster. Now, of course, all that's impossible because in reality, entering a black hole is a one-way ticket to oblivion. Basically, you get simultaneously stretched out into a long row of all your atoms and disappear into, well, we don't really know what you're disappearing into yet, but that long stretching out because of the gravitational pull and the difference in time. So your head is running at a different time to your feet. You're stretched out across time and space. It's called spaghettification. It's a good word, that, spaghettification. Of course, it means there is no universal time. Time's not the same everywhere. It runs at different rates. It's affected by speed, gravity. So we can't say, because it's, I don't know, 5:50 p.m. on the 23rd of November 1963 on Earth, it's going to be the same time everywhere. For a start, looking out into space, we see galaxies and stars that are many, many light years away. That means if we see a galaxy that is, say, 65 million light years away, we're seeing light that left the galaxy 65 million years ago. We're not seeing the star as it is now, or the galaxy as it is now. We're seeing it as it was 65 million years ago, just about the end of the dinosaur era. So you remember our broken glasses? You're going to recall that the glass could not be broken until it had been dropped, not before, okay? It has to be dropped, then it breaks. Well, there's another thing we have to include when looking at this. It's a funny word. It's called entropy. Now, entropy is a measure of how messed up things are. Everything ends up smashed in the end and broken, doesn't it? You know, unless we input some energy into things, they won't suddenly repair themselves or spontaneously construct themselves. A sandcastle will collapse through the wind and the waves washing over it, but the wind and the waves will never somehow construct a sandcastle from the same action. Okay, things tend to chaos, as they call it. Things break down and smash and break away. Yeah, even though that the wind and the waves blowing is random motions, you'll never get the wind and the waves suddenly construct a sandcastle. It's another important law in physics. It's called the second law of thermodynamics. Wow, what does that mean? Well, thermodynamics means moving heat. Thermo, heat, dynamics, moving around. And it's basically a word that refers to the fact that energy is moving towards becoming heat energy, and it's staying that way. So if entropy increases, things are getting more and more messed up, then that gives us a direction of time. In fact, many physicists believe that entropy is an important factor in what time is. Without entropy, there will be no time, and without time, there will be no entropy. It's more or less the same type of thing. Okay, it's the direction of time. So, given that we can't upset the order of cause and effect, and that entropy always increases, many believe this means that time travel is not possible. But that's by no means certain. So by manipulating the dimensions, bending space-time, we can see how time can be manipulated and that we can travel. In fact, we already are traveling in time. Just, it's always forwards. But let's imagine we did have a time machine that would mean we could travel across the universe and visit distant galaxies. It would also lead to some interesting possibilities and potentially odd situations. We've already seen that we could return at a time when our descendants were much older than us, but what if we traveled into the past? Supposing I jumped into my TARDIS right now and travelled back to the day that my great-granddad met my great-grandmother and did something that meant that they never met. I stopped them meeting, okay? My great-grandmother and great-grandfather met because my granddad got on a certain bus, which broke down, and he had to get off, and at the bus stop, he met my great-grandmother, and they started talking, and they agreed to go to the cinema, and so on and so on and so on. But I stopped that. Somehow I got into the bus station and I made another bus go out, which didn't break down. So my grandfather never got off the bus, never met my grandmother, or I could have done something a bit more violent and accidentally killed. Okay, what's going to happen? That's weird. Hang on, whoa. I go back in time. Okay, I got born. I went back in time. I'll go back and I killed my great-grandfather. So he dies. My grandfather was never born. My grandfather was never born. My great-grandfather never born. My father was never born. I was never born. So I couldn't go back in time to kill my great-great-grandfather because I didn't exist. So my great-grandfather met my great-grandmother and had my grandfather who had my father who had me, who went back in time to... Can you see how I've got a sort of what's going to happen? It's called the grandfather paradox. Yeah, they never married, never had children, so they couldn't have me, so I couldn't go back in time to stop them. So they did me, and they did have me, so I went back in time to stop them. Or let's try something a little bit more, I don't know, controversial. Let's kill Hitler. Let's go back. Stop Second World War. Okay, I'm going to go back. I'm going to shoot Adolf Hitler. Started World War II. So the World War II never happened. So I wouldn't know about Hitler then, so I wouldn't be motivated to go and kill him because Hitler would never have gone to power. There would never have been a war for me to get upset about, to want to go back in time and kill Adolf Hitler. So you can see time travel is full of potential problems. Maybe it's good we haven't discovered how to yet. I mean, particularly in America, you can think about what the Americans do. Have you seen their movies? They could really rewrite history, couldn't they? Gosh. Okay, so we've done an awful lot on time. Time for, no pun intended, time for us to do our Q&A session or talk about time. I'm sure that most of you found that fascinating. I'm sure you did. I mean, some of you have got some questions now because you don't... Hang on a minute, what did he say? Time slows down? What happens when you fall into a black hole? So if anyone's got anything to ask, I will put your pictures up on the screen so I can see you. So stick your hands up and maybe if I can get this so I can see all of you at once. That would be really good. No, oh, that's that one. We can go back to the Q&A. Gosh. Questions and answers. Right. Any questions, guys? Anything you want to talk about anything? And the whole 6 weeks. Anything you want to go over? Don't be shy. I shall unmute you all, and then you can tell me, ask me anything, talk to me. Tell me how brilliant you think I am. Tell me that you want to book some loads of lessons again. Anyone here now who used to hate physics now thinks physics is cool and great and fantastic? Oops, I've just realised I've gone through. Look at that, the whole 6 weeks in one great big lump. Do you remember doing all this? I can't believe that you haven't got anything that you want to ask me. Ah, here we go, that's better. A quicker way of getting that.
Wait, actually, I have a question.
Yeah, go on, far away. Let's have a chat about this. Go on.
See, like the grandfather paradox.
Yeah.
See, like if time travel was a thing and you went into the past and like made your grandfather and grandmother never meet, and like which means your dad and you were never born, and it would like which means you would have never changed anything, which means you would be alive still. Would you be in a loop for all eternity?
You could, couldn't you? I mean, you could set up, depending on how, because we haven't really done any practical experiments with time travel in that way, it could cause something to happen in the universe, which would mean that maybe, you're right, maybe this part of the universe would then get closed off, so there will be this constant churning of time going back on itself. And from outside of that, it would look like part of the universe was impenetrable, almost like a black hole type effect. Or it could be that when you travel back in time, one of the resolutions is if I go back in time, then from my point of view, the past has already happened. So no matter what I tried to do in the past, I couldn't change it. So if I went back in time to kill Adolf Hitler, I'd get shot myself, or I wouldn't kill him, no matter how much I tried. Or if I interfered with my grandparents on that bus, then it wouldn't stop the meeting because they would have met anyway, because I was part of my past. So it could be that, or it could be that you just blink out of existence, and your great grandfather, or your great grandfather was alive. Obviously, he's still there. And your great grandmother, they never met. Your father never was born, so you weren't born, and you just disappear out of time and space, and the universe carries on anyway. And there is no paradox in that sense, in that all you do is it'd be the equivalent really of you going back and ignoring your great grandfather but just shooting your granddad, your dad and yourself at the same time, and you'll just blink out of existence, and there'll be an alternative timeline, because there is a theory that says at any given time we are faced with choices and directions that things can go off in. So we've gone down this particular path where I do exist. If I go back in time and change that, then I never existed, and that other path would be followed. So there may not be a problem in terms of the laws of physics, but yeah, the universe is a really weird place. And if we start messing with it, it's only going to be just as weird as it was before, and we can have all sorts of things happen. So it'd be really interesting. I mean, we don't know that there could be time travelers out there, and the universe could be changing all the time. And I woke up this morning, and the universe was like it was. It seems the same as it was yesterday to me, but it could have been very different. But something changed overnight, but I changed with it, so I don't notice the change. If you can imagine an insect on a leaf on the tree, if I was to pick that tree up and move it across to another field and replant it, the insect wouldn't know the tree's changed. It'd still be on his leaf. It would have no effect. So I could change the entire universe, but because I changed with it, because my universe, my tree moved, me on my little leaf as an insect, I'm exactly the same as I was yesterday. I'm not even aware that things have changed, but they have. Or I could wake up on a different leaf And as long as I can see green and there's something to eat, I don't notice the difference. That's the way it is. Any more questions? I saw somebody saw a hand go up there. Who's that again?
Yeah, I have another question.
Yeah, go for it.
It's not the exact same question as the one before, but it's like similar. If time travel was real and we went into the future and I had a son and you killed yourself in the future, would it go into another paradox?
So if you went forward in time and shot yourself as an older person?
Yeah.
That would be really interesting. I've never thought of it going that way before. So I travel to 10 years' time, and I see my older self, and I shoot myself when I'm older. I think that wouldn't really cause a paradox, would it? That would be the only paradox it could think is if I knew I was going to shoot myself, I went forward to shoot myself, and I knew that was going to happen, and I changed my mind by the time I got to be the one being shot, and I went and hid, or I wasn't where I'm. Because I remembered, oh gosh, don't go to Southend-on-Sea next Wednesday because you'll get shot by yourself. So you go somewhere else. So your younger self turns up and you're not there. Yeah, that would be a bit of a paradox. Could I avoid my own death if I knew it was coming? Yeah, that's a good one, isn't it? I've changed my mind. I don't want to shoot myself. Yeah, that would make a basis of a pretty cool story, actually, wouldn't it? Traveling in time to shoot your future self. I like that. Yeah. Oh, yeah, that would be an interesting paradox. Okay, who else has got their hand up? I saw some hands going up. Can't be the only ones who want asked questions.
I accidentally put my hand up, so.
All right, that's all right, no worries. So, we have had, gosh, how long have we had now? 6 weeks. We've had 6 of these sessions. So who has enjoyed them?
I have.
Good.
I have.
Yeah, brilliant. That's the main thing.
Yeah, me too.
Oh, brilliant. The main thing was I wanted you to enjoy this because I love physics, I love science. And
I wish we would have 1,500 and many lessons.
Well, do you know what? In one theory, there's an infinite number of universes out there.
Maybe.
Yeah, there's as many universes as there are possibilities, and they're very tiny possibilities. We're not talking about a universe where there's 2, where there's one where I'm the Prime Minister and there's one where I'm not the Prime Minister. There's so many different things that could happen. Things like I picked this up and had a sip, and I spent a fraction of a second longer sipping it in one universe than the other. So every time I do something, I create a new universe. So there's an infinite number of universes. One of them, I'm incredibly rich and happy and handsome and good looking, like I am in this one. And then the other one, I'm horribly, ill. And there's other universes where I died before, when I was a baby. And other universes where I'm going to live to be 200. And other universes where, I don't know, all sorts of things happen. Or just literally, I put a different tie on. So there's a universe for every single tie I've got. And a universe for no tie. And there's a universe for all the waistcoats I've got. And a universe for all the waistcoats with all the ties. So by the time all those decisions are panned out, there's millions and billions of universes. Oh, another hand going up? Or was that an accident? Well, I'm going to say, because we're cracking on towards 11 o'clock, time's catching up with us. Time's catching up with us. So over the last 6 weeks, what have we done? We've found out how to leave the Earth. Found out about the solar system, the galaxy, the universe. We found out about life, and we've done a very, very, very little bit, a tiny fraction of time, which I think you'll find is probably the most interesting but difficult session that we've had with time, because it's such an amazing thing. But space and time are only part of the story of science. Okay? Science, oops, let's get rid of that. Science includes all of physics, chemistry, biology, and maths, but also history. geography, languages, humanities, everything. Science involves collaboration across national boundaries, countries working together to further our knowledge and develop medicines, technology. It gives us all so much. And I really hope you found these last few weeks interesting and entertaining, and more importantly, inspiring. So even if you don't want to or can't choose to study science subjects, please keep an interest in it. Not only the science itself, but the need to follow evidence and facts when making decisions and choices. Evidence is what it's all about. So thank you for coming with me on our voyage. It really was a genuine pleasure to travel with you, and I wish you all an amazing future. And who knows, perhaps we'll meet again as you continue your own journey across the universe.
I have one more question.
Yes, go on.
See, like, the theory about, like, your actions can make more, like, universes and galaxies and stuff.
Yeah.
See if that isn't true. Well, and, like, some point in the future, will we ever discover the whole entire, like, universe?
Oh gosh, I think the universe is so big and so massive that I think it'll be like a goldfish trying to explore the Pacific Ocean from his goldfish bowl. I think we're going to be limited to our own particular goldfish bowl. Now that doesn't mean that we can't go immense distances ultimately. And who knows, maybe we will invent a way of getting across the universe almost instantaneously, but it's going to cause problems, because if we do start flitting around all over the place, we are going to end up spread across time. So it's going to be as if you can think what time travel is to someone in the 21st century in terms of being able to do it, would be like explaining to a caveman about fighter jets and fast machines like that. It's a complete concept. You have to get through with the rules and how it works and everything. So early man knew his little bit of land and the animals around him, and now we're saying, you know, trying to explain to him that we can travel to the moon and that sort of thing. It's going to be probably a million times more of a leap. And it's not just the thing with science. It's not just the technology and the facts and the knowledge. It's the change to the way we think and feel. You think about how we are now, when we've got iPads and computers and cars and houses with electricity and everything. Think how we've had to adapt our lives to people that didn't have electricity. They had to have candles, and we didn't have central heating. We had fires in a hut that was little more than a mud hut. All those sort of things. And think about how we've had to adapt simply to get over this COVID crisis. We've all changed our lives, don't we? We go to school online. You know, we have to plan our shopping, all sorts of things. So just a minor change like that affects not just what we can do, but how we think and how we see the universe. And that's the thing about science. That's why I said it's not just the technology. It's not just, oh, we've got a gadget that does this and we've got a medicine to do that. If you come up with a medicine that cures death, what are we going to do with all the people? If everyone's going to live forever, what's the hurry to invent things? What's the hurry to create music? You know, if we got rid of a lot of what happens in the world, we would change what we do. If you knew you were never going to die, what's the hurry to do anything? And how are we going to feed people in an ever-increasing population? We're going to say no more children. Everyone's living forever now. You can't have children. Well, I want children. If you're going to come up with something that allows us to travel instantly around the planet, like a beaming someone on Star Trek, people are going to be zapping all over the place. So all of a sudden, you could have everyone decides to go to the seaside that day and beams in. You can go anywhere. What you do, we're going to have to change how we do things. So if we get time travel, we have to have laws and rules that can prevent us from going back and killing our grandparents and all that sort of thing. So we're setting up all these paradoxes everywhere. The universe could basically collapse in on itself or blow up or something. You know, it's going to change the way we actually behave as well. So yeah, I've gone off on a tangent there, but this is the thing about science. It affects not just what we can do, it affects how we think and how we act about things. So yeah, very deep and meaningful. Okay, right. Any more questions at all? So it really is time to go, and I could talk to you guys for hours and days and weeks because you have been brilliant. I've had 3 of these sessions running side by side, and this was the bee's knees, this one. I've really enjoyed it. Some fantastic questions, some really challenging, some really thought-provoking. But like I said, as long as you've enjoyed it, and if you ever want any help with science, if you go to Tutorful, you can contact me via Tutorful. You've got my website, you've got my YouTube channel there. I'm still posting videos every so often. These are all going to go online, so if you want to revisit this one will probably end up online, this particular lesson, which will be good. So yeah, go for it. But I really have to go, guys. Time marches on. So last time, thank you very much indeed. I've really enjoyed it. And just remember, keep wondering about that universe. Cheers, guys.